Out in the deep black, James Webb just photographed something 13 billion light-years away that the laws of physics say cannot be there. A ring of galaxies wider than anything known. A wall of light older than time should allow. A shape so massive it breaks the rules cosmologists wrote to explain the universe. If mysteries like this pull you in, hit that subscribe button and stay with us. Tonight we travel to an impossible ring, a wall of ancient galaxies, and the silent void that may be swallowing everything we know. Prepare yourselves. We begin. It was a quiet Tuesday morning at the Space Telescope Science Institute in Baltimore. A handful of researchers sat with coffee, waiting for a routine data dump from James Webb. Nothing special was expected. Just another deep field image from a patch of sky near the constellation Boötes. Then the file opened. The lead astronomer leaned closer to her screen. She stopped talking. Her colleague across the room noticed the silence and turned around. Within a minute, 3 more people had gathered behind her chair. No one said a word. What they were looking at should not have been there. Stretched across the image was a pattern of galaxies arranged in a near-perfect curve. Thousands of them, glowing in faint infrared, pulled across a span of sky so wide it took Webb's cameras multiple passes to capture the full shape. And that curve was not a cluster. It was not a chance alignment of foreground and background objects. It was a single connected structure, sitting at a distance of roughly 10 billion light-years. Translation: they were seeing something that formed when the universe was still a toddler. One of the researchers whispered a single sentence. This breaks the model. Because according to the rules cosmologists have trusted for almost a century, a structure this large simply cannot form in the time available. The universe, as we understand it, is only about 13.8 billion years old. Gravity works slowly on cosmic scales. Pulling galaxies into shapes of this magnitude should take far longer than the universe has existed, and yet there it was, sitting calmly in the data, daring them to explain it. Within hours, the image was shared on an internal server. By the end of the day, astronomers in Europe, Japan and Chile had downloaded it. By the end of the week, private group chats among cosmologists were on fire. Nobody wanted to go public yet. They wanted to double-check, triple-check, make sure this was real and not some optical trick caused by gravitational lensing or camera error. But every check came back the same. The structure was real, the distance was real, the size was real. And the size was the terrifying part. If you took 1,000 of our Milky Way galaxies and lined them up end to end, you would still fall short of the width of this object. It stretches across a portion of sky equivalent to dozens of full moons placed side by side. Whatever process created it, it happened early, too early, faster than any current theory allows. One astronomer compared it to walking into a forest and finding a tree that had grown 10 miles tall in a single afternoon. Not impossible in a storybook, impossible in reality. And this was only the first image. Webb had been scheduled to survey many more fields like it over the following months. If one area of the sky held a structure like this, what were the others hiding? By the time the preliminary report reached Anthropic's peer review board, a quiet word had started circulating through the community. A word nobody wanted to say out loud. Wrong. Our model of the universe might be wrong, and what Webb saw next made it worse. Before we go further, you need to understand why astronomers reacted the way they did. Because in everyday life, the word impossible gets thrown around casually. In cosmology, it has a specific meaning, and to grasp that meaning you have to understand a rule called the cosmological principle. Here is the rule in plain language. If you zoom out far enough, the universe should look roughly the same everywhere, not identical down to the last star, but statistically similar. Galaxies should be spread out in a mostly even foam, some regions denser, some emptier, but averaged over huge distances. Everything should balance out. Think of it like sprinkling pepper on a plate of soup. Up close, you see clumps. Pull back, and the pepper looks evenly scattered across the surface. That is how the universe is supposed to behave on the larger scales. This rule is not a guess. It is the foundation that nearly every equation in modern cosmology rests on. Einstein's field equations assume it. The Big Bang timeline depends on it. The way we calculate the age of the universe, the amount of dark matter, the rate of expansion, all of it relies on the idea that no region of space contains structures too large to have formed by now. There is even a number attached to this rule. Cosmologists call it the upper limit of structure formation. It sits at around 1,200 million light years. Any single connected object bigger than that should not exist, because gravity has not had enough time since the Big Bang to assemble anything larger. Now stop and picture that number, 1,200 million light years. A distance so vast that light itself takes longer to cross it than the entire history of life on Earth. That is supposed to be the ceiling, the absolute maximum. The structure Webb found is wider than that ceiling. Not by a little, by a lot, and it is not alone. Over the past 2 decades, astronomers have been finding more and more objects that break this limit. Each time one was discovered, the community argued. Maybe it was a statistical fluke. Maybe the measurements were off. Maybe it was a chance alignment. But every time a new telescope came online, the forbidden objects kept showing up. Bigger, more defined, harder to explain away. Webb was supposed to settle the debate. With its sharper eye and infrared vision, it could measure these distant structures with precision that older telescopes could only dream of. The hope was that Webb would reveal the forbidden giants were illusions. Instead, Webb confirmed them and found new ones. This puts cosmologists in an uncomfortable spot. If the cosmological principle is wrong, or even partially wrong, then the entire framework for understanding the universe starts to wobble. Every calculation based on it might need revising. Every prediction about the fate of space and time could shift. One researcher put it bluntly at a conference in Chile. If these structures are real, we have been measuring the universe with a broken ruler. A broken ruler. That was the phrase that stuck. And when you have been measuring something with a broken ruler for 100 years, you do not know how wrong your numbers actually are. You only know they are wrong somewhere. The first forbidden giant now has a name, and its shape is even stranger than its size. In early 2024, a team of astronomers led by a young researcher at the University of Central Lancashire announced something that stopped the field cold. They had found a ring. Not a ring of planets, not a ring of stars, a ring made of galaxies. Thousands upon thousands of them, arranged in a circular shape so vast that calling it a ring almost sells it short. Its diameter stretches 1.3 billion light-years from edge to edge. To put that in words, you can feel if our Milky Way galaxy were a single grain of rice. This ring would be a circle wider than a football stadium built from those grains. They named it the Big Ring, a plain name for something so wild. The discovery began when the team was studying a distant quasar, a type of brilliant object powered by a supermassive black hole at the center of a far-off galaxy. Quasars act like cosmic flashlights. When their light travels across billions of years to reach us, it passes through whatever lies between us and them. By carefully studying the way that light dims and shifts, astronomers can map the invisible structures in its path. That is how the ring revealed itself. A perfect curve of absorption signals lined up across the dark. At first, the team thought they had made a mistake. Rings of that size should not form in nature. Gravity pulls matter into blobs, webs, and filaments, shapes with no reason to be circular. A ring suggests something organized, something with symmetry. And symmetry on a scale of 1.3 billion light-years is not something current physics can produce. They checked the data for months. They ran simulations. They tried to explain it as a trick of perspective, a flat band of galaxies that only looked circular because of the angle we view it from. But the numbers refused to cooperate. The ring was real. It was circular, and it sat roughly 9.2 billion light-years from Earth. Think about what that means. The light from this ring left home when the universe was less than half its current age. Whatever force shaped it was already at work long before our sun, our solar system, or even our galaxy as we know it came into being. Nobody has a confirmed explanation yet. That is important. This is not a solved case. Theories range from mundane to radical. Some suggest the ring is a cosmic coincidence, a statistical fluke that looks meaningful but is random. Others propose it could be the imprint of something called a baryon acoustic oscillation, a kind of sound wave frozen from the early universe. But the Big Ring is much larger than any predicted baryon oscillation, which makes that theory a stretch at best. Then come the wilder ideas. A few physicists have suggested the ring could be evidence of cosmic strings, hypothetical ultra-thin cracks in space-time left over from the first seconds after the Big Bang. Others whisper about echoes from a previous universe, scars from a cosmic bounce that may have come before our own beginning. None of these ideas are proven. All of them require new physics, and the Big Ring is not even the strangest shape Webb and its companion telescopes have uncovered, because sitting near the same region of sky is something even older, something that looks less like a circle and more like a wound. A few years before the Big Ring was announced, the same research group found something else in roughly the same corner of the sky. They called it the Giant Arc, and true to its name, it curves across space like a cosmic crescent. The Giant Arc measures 3.3 billion light-years from tip to tip. Let that number settle for a moment. That is almost 3 times the size of the Big Ring. It is wider than any structure humans have ever confirmed, and it sits about 9.2 billion light-years away at roughly the same distance as the ring, raising a question that has made cosmologists nervous. Why is this region of the sky so packed with forbidden giants? The arc was discovered using the same quasar technique. A careful survey of distant light passing through intervening gas revealed a crescent-shaped pattern of galaxies and cold hydrogen clouds. Not a random scatter, not a typical web, a curve, clean, continuous, and unmistakable. When the team submitted their findings to the peer review process, the reaction was intense. Some reviewers demanded additional verification, others asked for independent surveys to confirm the shape, and at every step, the arc held up. More data came in, more galaxies were identified as part of the structure. The curve grew sharper, not weaker. And here is what makes the arc particularly troubling. Unlike the Big Ring, which has that elegant circular symmetry, the arc is lopsided. It bends in one direction. It has a beginning and an end. It looks carved, almost sculpted, by a force that operated in a preferred direction across an enormous region of space. This matters because the cosmological principle, the foundational rule we talked about earlier, says the universe should not have preferred directions on large scales. There should be no up, no down, no east, no west when you zoom out far enough. But the giant arc seems to have all of those things. It points, it sweeps, it orients. If it is real, and every check says it is, then something in the early universe was not symmetric. Something pulled matter one way more than another, and whatever that something was, our current physics does not describe it. The team compared the arc to finding a signature carved into a mountain. You can argue that erosion made it. You can argue that chance aligned the rocks, but the longer you stare at it, the harder it becomes to deny that something deliberate, or at least organized, was involved. Some astronomers have tried to save the standard model by suggesting the arc might not be a single structure. Maybe it is 2 or 3 smaller features that happen to line up from our viewing angle. But the distances and velocities of the galaxies within the arc suggest otherwise. They move together, they are bound by the same cosmic flow, they are one thing, and one thing that big, that early, that shaped, is a scientific earthquake. The researchers who discovered the arc have been cautious in their public statements. They avoid using words like impossible. They prefer phrases like challenging to explain. But behind closed doors, at conferences where the press is not allowed, the conversations are blunter. If the arc is real, the textbooks need rewriting, and the rules they break are older than the telescopes that found them. To understand why these discoveries feel like the ground shifting under cosmology's feet, you have to understand the age of the idea they threaten. The cosmological principle is not a modern invention. Its roots stretch back almost 100 years to Albert Einstein himself. When Einstein wrote down his equations of general relativity in 1915, he faced a problem. His math could describe an expanding universe, a contracting universe, or many other possibilities. To narrow things down, he needed an assumption. He chose the simplest one available. He assumed the universe on the larger scales is uniform, smooth, the same in every direction, from every viewpoint. This assumption made the equations solvable. It also felt philosophically comfortable. It matched a belief scientists had carried since Copernicus, that Earth holds no special place in the cosmos. If Earth is not special, then no location is special. And if no location is special, the universe should look the same wherever you stand. For decades, this idea held beautifully. Observations of distant galaxies seemed to confirm it. The cosmic microwave background, the faint glow left over from the Big Bang, appeared almost perfectly uniform, with only tiny ripples from place to place. Everything suggested that Einstein's simple assumption was correct. Based on this principle, cosmologists built what is now called the Standard Model of Cosmology, sometimes shortened to lambda CDM. It describes how the universe began, how it evolved, and how it will end. It predicts the amount of dark matter, the behavior of dark energy, and the distribution of galaxies. Every major result in the field, from the age of the universe to the composition of space, flows from these foundations, and this model predicts a ceiling on how large any single structure can grow. The reason is straightforward. Gravity works by pulling matter together over time. Starting from the tiny density differences visible in the cosmic microwave background, gravity has had about 13.8 billion years to sculpt the cosmos into the structures we see today. That is a long time, but not infinite. There is a limit to how much sculpting can happen in that window. Run the simulations, and they agree. The largest structures should not exceed roughly 1,200 million light-years across. Anything bigger would require more time than the universe has had, or more gravitational pull than the available matter can provide. The Big Ring breaks this limit slightly. The giant arc breaks it by nearly 3 times. and other structures, which we will visit shortly, break it by factors that are almost embarrassing. This is where the word crisis starts getting used in papers, not as exaggeration. As a technical description, a situation where observations and theory disagree so sharply that one of them must be wrong. The uncomfortable part is the observations are hard to argue with. They have been checked, rechecked, and confirmed by independent teams using different instruments. The data is solid, which means the theory is the suspect. Some cosmologists have started proposing modifications. Perhaps the early universe had a brief period of rapid growth that we have not accounted for. Perhaps dark matter behaves differently than we thought. Perhaps the cosmological principle only applies on scales larger than we have yet measured, and we need to look farther to find true smoothness. But none of these fixes are small. Each one rewrites a piece of the foundation, and to dig deeper we need a telescope that sees what Hubble could not. For more than 30 years, the Hubble Space Telescope was humanity's window on the deep universe. It gave us the Hubble Deep Field, one of the most profound images ever captured. A tiny speck of sky, no bigger than a grain of sand held at arm's length, revealed thousands of distant galaxies stretching back billions of years. Hubble was revolutionary, but Hubble had a wall it could not climb. That wall was light. As the universe expands, the light from distant objects gets stretched. A wave that started as visible light, the kind your eyes can see, slowly gets pulled longer and longer until it becomes infrared. By the time light from the oldest galaxies reaches us, almost all of it has been stretched into infrared wavelengths. Hubble was built mostly for visible light. It could peek a little into the infrared, but not far, not deep enough to catch the earliest galaxies clearly. Those ancient lights slipped past Hubble's vision like whispers in a language it could not hear. Webb was built to hear those whispers. James Webb is, at its heart, an infrared telescope. Its mirror is made of 18 gold-coated hexagonal segments that together form a reflective surface 6.5 meters across, roughly the width of a 2-story house. Compared to Hubble's mirror, which is a little under 2.5 meters, Webb collects about 6 times more light. And because it sees infrared, it can detect the stretched glow of galaxies so distant, so ancient, that their light has been travelling for more than 13 billion years. There is a catch though. Infrared light is heat. Anything warm emits it. That means Webb itself has to be incredibly cold, or its own glow would drown out the faint signals it is trying to catch. To solve this, engineers built a 5-layer sun shield the size of a tennis court and sent Webb to a point about 1 million miles from Earth. At that distance, the Sun, Earth and Moon all sit on the same side of the sun shield, letting the telescope stay at a frigid temperature close to minus 370 degrees Fahrenheit. In that deep cold, Webb sees what no other instrument can. The first deep field image Webb released in July of 2022 covered the same tiny patch of sky as one of Hubble's old deep fields. Where Hubble had shown thousands of galaxies, Webb revealed tens of thousands. Fainter, redder, more distant. Galaxies that had been invisible for all of human history suddenly blinked into view. And in those images, astronomers began noticing oddities. Galaxies that looked too mature, clusters that seemed too organized, shapes that did not fit the expected timeline. Many of the strange structures we will visit in upcoming chapters were spotted or confirmed because Webb's infrared eye could pull them out of the cosmic haze. Without Webb, the Big Ring would still be a hint in the data. The giant arc would still be disputed. The impossibly old galaxies we'll soon meet would still be invisible. Webb has not just added new pictures to our album of the cosmos, it has changed what counts as picturable. Every week, new Webb data arrives at astronomy institutes around the world, and every week, the pile of puzzles grows. Because the trick that lets Webb find these giants is also the trick that has exposed the deepest cracks yet. To grasp why Webb has been so transformative, we need to spend a moment on the trick that makes its observations possible. Astronomers call it redshift, but that word sounds more technical than the idea really is. Imagine an ambulance speeding past you with its siren on. As it approaches, the siren sounds higher pitched. As it moves away, the pitch drops. The sound waves are the same coming out of the siren, but your ears hear them differently depending on whether the source is moving toward you or away. Light does the same thing. When a galaxy moves away from us, the light waves it emits get stretched. Waves that started blue shift toward red. Waves that started red shift into infrared. Waves that started infrared shift into even longer, invisible forms. The faster the galaxy is moving, the more the light stretches. The more distant the galaxy, the faster it is moving, thanks to the expansion of the universe. So distance and redshift are tightly linked. This gives astronomers a cosmic measuring tape. By carefully measuring how much a galaxy's light has been stretched, they can calculate how far away it is and how long ago its light left home. Here is where it gets strange to think about. When you look at a galaxy 5 billion light years away, you are not seeing it as it is now. You're seeing it as it was 5 billion years ago because its light took that long to reach you. Every telescope is a time machine. Every distant object is a snapshot of the past. Webb, by reaching wavelengths other telescopes cannot, can see objects whose light has been travelling for over 13 billion years. That puts us face to face with the universe as it looked just a few 100 million years after the Big Bang. A cosmic infancy nobody had ever witnessed directly. And this is where Webb's discoveries become so threatening to the standard model. When Webb looks at that infant universe, it sees things that should not be there. Galaxies that look too big, too bright, too organized, too complete. According to standard predictions, galaxies in the first few 100 million years should be small, messy and dim. Gas clouds collapsing, stars just beginning to form, everything a chaotic work in progress. The first real galaxies should be faint smudges, with maybe a few % of the mass of today's average galaxy. But Webb has found galaxies from this era that are fully formed. Well-structured disks, large populations of old stars, masses that should have taken billions of years to accumulate, already present when the universe was less than 1 billion years old. Some of these early galaxies appear to be spinning neatly, with organized arms and defined cores, not the tumbling, chaotic blobs the models predicted, calm, grown-up structures where only infants should exist. To explain this, astronomers have been forced to consider ideas that were once fringe. Maybe star formation in the early universe was vastly more efficient than thought. Maybe dark matter clumped faster. Maybe the timeline of cosmic history has been miscalculated from the start. Each possibility opens new doors. Each one closes old ones. And the person whose discovery first cracked the wall open was not a seasoned professor, but a student barely out of her 20s. Every now and then, a major scientific shock begins with someone young, stubborn, and unafraid to question authority. In this case, her name is Alexia Lopez. In 2021, Alexia was a PhD student at the University of Central Lancashire in the United Kingdom. She was working under the supervision of Professor Roger Claus, an astronomer already famous in the field for discovering the huge, large quasar group, another oversized structure that had raised eyebrows years earlier. Alexia's job was to sift through quasar absorption data, looking for patterns in how distant light was being filtered by intervening gas. It was slow, detail-heavy work. Most graduate students in astronomy spend years on projects that never produce headline-worthy results. Alexia's project could have ended that way too. But while she was processing her maps, she noticed something odd. A curve, not a scatter, not a random cluster. A long, smooth curve of absorption signals sweeping across an enormous region of sky. At first she assumed it was an artifact, a kind of processing error that sometimes creeps into astronomical data. She cleaned the data. The curve remained. She tried different statistical methods. The curve remained. She expanded the sample. The curve grew longer, still smooth, still coherent. She brought the finding to her advisor. He was skeptical, as any good scientist should be. Together they ran more tests. They compared the signal to known patterns. They checked whether gravitational lensing, the bending of light by massive objects in the foreground, might be creating the illusion of a shape that was not really there. Nothing panned out. The shape was real. When the team published their discovery of the giant arc in 2021, the astronomy world reacted with cautious attention. Some researchers praised the work. Others demanded more proof. A few outright doubted that a structure so large could be physical at all. Then, in 2024, Alexia returned with the big ring. Same general region of sky, different shape, same problem for the standard model. Suddenly the doubters had a second forbidden giant to explain, not one. The two structures sit close enough in space that their coexistence raises an uncomfortable question. Are they related? Is this region of the sky unusual, or is every region of the sky like this, and we simply have not looked carefully enough yet? Alexia has become something of a quiet celebrity within cosmology circles. She speaks at conferences with measured calm, presenting her findings without exaggeration. She does not claim to have overthrown Einstein. She presents the data and lets the data speak, which ironically makes her case harder to dismiss. In interviews, she has described the moment she first realized the arc was real as both thrilling and unsettling. Thrilling, because every scientist dreams of discovering something unexpected. Unsettling, because the implications might undo decades of carefully built theory, including work done by her own mentors. What matters about her story is that it reminds us of something important. Some of the biggest shifts in our understanding of the universe do not come from seasoned experts defending their life's work. They come from new eyes looking at old data and daring to say, wait, this does not look right. Her tools to detect these giants are as clever as her instincts. The method Alexia Lopez and her team used to find both the giant arc and the big ring is one of the most elegant tricks in modern astronomy. It turns the brightest, most violent objects in the universe into flashlights pointed across billions of light years of empty space. Those flashlights are called quasars. A quasar is the glowing heart of a distant galaxy, powered by a supermassive black hole feeding on surrounding gas. As gas spirals into the black hole, friction heats it to temperatures so extreme that it outshines the entire rest of the galaxy around it. From Earth, a quasar can look like a single brilliant point, easily mistaken for a star, even though it is actually the luminous core of a galaxy billions of light years away. Some quasars are so bright that their light can be seen across the entire observable universe. That brightness is what makes them perfect for the trick. Here is how the method works. When light from a quasar leaves its source and travels toward us, it passes through everything in its way. Dust clouds, cold gas, sheets of galaxies, invisible filaments of hydrogen. At each layer, certain wavelengths of the light get absorbed while others pass through. The pattern of absorption leaves fingerprints in the quasar's spectrum, a kind of cosmic barcode that tells astronomers what the light encountered on its journey. By studying thousands of quasars scattered across the sky, researchers can build a three-dimensional map of the invisible material sitting between us and those distant lights. It is like shining flashlights through fog and using the shadows to figure out the fog's shape. This is how the giant arc and the Big Ring were found. The team did not need to see every galaxy in those structures directly. They only needed to see the imprint those galaxies left on the light of quasars behind them. Specifically, they looked for absorption caused by ionized magnesium, a common element that fingerprints cool gas clouds in distant galaxies. When Alexia plotted out the positions of magnesium absorbers in her data, the shapes emerged. A curve, a ring, patterns no random scattering of galaxies should produce. The beauty of the method is that it reveals structures that would otherwise be invisible. Many of the galaxies contributing to the arc and the ring are too faint to be seen directly with current telescopes, even Webb. They are ordinary galaxies, not blazingly bright, and they sit so far away that their own light is lost in the cosmic glare. But their gas clouds block the quasar light, and that blockage is detectable. It is a bit like trying to spot a person standing in a dark room. You cannot see them directly, but if you shine a flashlight past them, their shadow appears on the wall. The method does not show you the person, it shows you the shape they cut out of the light. The result is a sap of the universe drawn in shadows. This technique has been used for decades, but only recently have the survey sizes grown large enough to reveal structures on the scale of billions of light years. Projects like the Sloan Digital Sky Survey have mapped hundreds of thousands of quasars. Each one is a flashlight. Together, they illuminate a cosmic landscape nobody knew existed. And what those shadows reveal is an element that glows with particular brilliance. Out of all the elements in the universe, magnesium plays a quiet but crucial role in helping astronomers detect distant structures. That might sound surprising. Magnesium is not exotic. It is the stuff inside lightweight bike frames, the ingredient that makes antacids work, the metal that burns with a dazzling white flame when it catches fire. In space, magnesium exists as ionized atoms floating in cool gas clouds around galaxies. These atoms absorb light at very specific wavelengths, creating sharp, narrow dips in the spectrum of any bright object whose light passes through them. These dips are so precise, so clean, that they serve as almost perfect fingerprints. Astronomers call this signature Magnesium 2. It sits at wavelengths that Webb and other telescopes can pick out with high accuracy, even across enormous cosmic distances. Here is why this matters for our story. When a quasar's light passes through a galaxy on its way to Earth, the cool gas in that galaxy leaves a Magnesium 2 fingerprint on the light. By measuring how much the fingerprint has been redshifted, astronomers can figure out exactly how far away the intervening galaxy is. By counting the number of fingerprints in a region, they can estimate how many galaxies are there, and by mapping their positions, they can reveal the shape of whatever structure those galaxies belong to. Magnesium became the flashlight powder, the dust that makes the invisible visible. In the data that revealed the Big Ring, the team identified dozens of these magnesium fingerprints, each one corresponding to a distant galaxy lying along a near-perfect circular arc around a background quasar. That pattern could not happen by chance without staggering odds. When statisticians ran the numbers, The probability of so many galaxies aligning randomly in that shape came out to less than 1 in 100,000. Translation: either the universe played an absurd cosmic lottery, or something organized those galaxies into that ring. The giant arc was detected the same way. Magnesium signatures in the spectra of quasars outlined a curve spanning thousands of galaxies, sitting at roughly the same distance. Again, the odds against random arrangement were astronomical. What is fascinating is that without magnesium, these shapes might never have been noticed. If astronomers had relied only on direct imaging, the faint galaxies that form these megastructures would have blended into the background noise. Only because cool gas clouds around each galaxy left a detectable chemical signature did the patterns emerge. It is a humbling reminder. Much of the universe's deepest structure is not shining brightly. It is quiet, dim, hidden in the spaces between the lights, and we only find it because ordinary elements like magnesium, produced in the cores of dying stars, happen to absorb light at wavelengths we can read. Every magnesium atom drifting in those distant clouds was forged inside a star that lived and died long before Earth formed. When that star exploded, it scattered its metals into space, where they cooled and collected in gas halos around galaxies. Billions of years later, those atoms absorbed the light of a quasar, and billions of years after that, the absorbed signal reached a telescope built by humans and told us a secret about the shape of the cosmos. The chain of events is so long, so improbable, and so specific that it borders on poetic. But the poetry is not what matters to cosmologists. What matters is that the method works, and the shapes it reveals keep getting larger. Because before the ring and the arc, there was another wall that started it all. The shocks did not begin with Webb. They did not begin with the big ring or the giant arc. The first serious crack in the standard model of cosmology appeared years earlier, when astronomers using the Sloan Digital Sky Survey reported a structure they named the Sloan Great Wall. This was in 2003. The team, led by astronomer Richard Gott, was mapping the distribution of galaxies in a large section of the sky. As they worked, a pattern emerged, a vast sheet of galaxies stretching across the data like a massive cosmic partition. When they measured it, the results startled them. The Sloan Great Wall stretches about 1.4 billion light-years across. At the time, it was the largest known structure in the observable universe, and it sat comfortably beyond the supposed 1,200 million light-year limit for structure formation. In cosmology terms, that was already a red flag. Not a catastrophic one, but enough to make theorists uncomfortable. Some argued the Sloan Great Wall might not be a single connected structure, but rather a chance alignment of 2 or 3 smaller superclusters. Others pointed out that the definition of a structure depends on how you draw the boundaries, and that different statistical methods gave different sizes. For a while, the debate stayed academic. The Sloan Great Wall was unusual but explainable with enough hand-waving. Then, slowly, other walls and superclusters started appearing. The Claus-Camposano Large Quasar Group, the huge large quasar group discovered by Roger Close, Alexia Lopez's future mentor in 2013. Each new find pushed the size limit further. Each one was met with the same arguments. Maybe it is not really one structure, maybe the data is misleading. The trouble was the objections kept weakening as the data kept improving. Bigger surveys, better instruments, more galaxies, more quasars, more precision, and every improvement made the megastructures look more real, not less. The Sloan Great Wall itself has been re-examined many times since its discovery. Different teams have measured its size slightly differently, but all agree on its existence. It is real, it is enormous, and it refuses to fit into the simple story of slow, uniform cosmic evolution. For viewers new to this topic, it is important to grasp the scale here. The Milky Way, our galaxy, is about 100,000 light-years across. Our local group of galaxies, which includes Andromeda and a few dozen smaller companions, is roughly 10 million light-years across. The Virgo supercluster, the larger neighbourhood our galaxy belongs to, spans about 110 million light-years. The Laniakea supercluster, an even grander structure we discovered in 2014, stretches about 520 million light-years. Laniakea is already close to the theoretical maximum. The Sloan Great Wall is nearly 3 times larger. The giant arc is more than 2 times larger than that. And beyond the giant arc, there is something even bigger that we're about to meet. Each of these was once the largest known structure. Each held that title until something bigger was found. And the pattern suggests a trend nobody wants to confront directly. Maybe the universe contains structures of any scale, and the only limit is how far our instruments can see. If that is true, the whole notion of cosmic smoothness collapses. And when one particular structure came to light in 2013, the collapse accelerated. In 2013, astronomers studying data from gamma-ray bursts noticed something that seemed too large to be real. A distribution of bursts that clustered unusually in a region of the sky spanning parts of the constellations Hercules and Corona Borealis. When they measured the distances to these bursts, they realized they were looking at a structure with a span that defied belief. They called it the Hercules-Corona Borealis Great Wall, and its estimated length is about 10 billion light-years. Read that again. 10 billion light-years. That is more than 70% of the distance across the entire observable universe. It is a structure so large that if you tried to cross it at the speed of light, most of the history of the cosmos would pass before you reach the other side. Gamma-ray bursts are the most powerful explosions known to science. They occur when massive stars collapse into black holes, or when neutron stars collide, and they release more energy in a few seconds than the sun will emit over its entire lifetime. Because they are so bright, they can be detected from enormous distances, serving as tracers for the galaxies where they originate. When astronomers plotted the positions of gamma-ray bursts across the sky, most regions showed an even scattering, as the cosmological principle predicts. But in the Hercules-Corona Borealis region, the bursts clumped. There were too many in too tight a pattern for random chance to explain. The conclusion was unavoidable. The bursts marked a region where galaxies were densely packed together, forming a structure of almost unimaginable size. Some cosmologists immediately pushed back. They argued that the sample of gamma-ray bursts used was too small to draw conclusions. They pointed out that gamma-ray bursts are rare and that their distribution might not perfectly trace the underlying galaxy distribution. A few suggested the whole thing was a statistical illusion. But over the years, additional data has come in. More bursts have been detected. The pattern has held. The Hercules-Corona Borealis Great Wall, whatever it is, appears to be real. If it is real, it is roughly 8 times larger than the theoretical maximum for structure formation. 8 times. Not a rounding error, not a minor overshoot. A violation of cosmological rules so severe that mainstream theorists have largely refused to engage with it. Some call it the ultimate challenge to the cosmological principle. Others quietly hope better data will shrink it or dissolve it into smaller components. But for now, the wall stands in the literature, a silent giant that nobody can fully explain away. Think about what it means if the wall is genuine. a filament of galaxies so vast that even travelling at the speed of light, you could live 1 billion lifetimes and barely see a fraction of it. A structure that would take more time than the universe has existed to assemble under normal gravity. A feature of the cosmos that our best models simply cannot produce. And unlike the Big Ring or the Giant Arc, which have distinct shapes, the Hercules-Corona Borealis Great Wall is more of a dense clustering, a region of elevated density rather than a clean geometric form, which in some ways makes it more mysterious. Why this region? Why this much? Why here? Nobody knows. But Webb is beginning to answer related questions by examining galaxies that, on their own, should not exist. Large structures are not the only thing rattling cosmologists. Some of the most disturbing Webb discoveries are individual galaxies, too old-looking for their age, too massive for their youth, too complete for the moment in history where Webb finds them. When Webb looks at the early universe, roughly 300 to 600 million years after the Big Bang, it should see chaos. Clumps of gas collapsing into tiny proto-galaxies, bright flashes of the first stars forming, small irregular shapes with no clear structure. Instead, Webb has found galaxies that look like they could belong in our neighbourhood today. One example caused a stir in early 2023. A galaxy nicknamed Maisie's Galaxy, after the daughter of the astronomer who found it, sits at a distance where we're seeing it as it was about 390 million years after the Big Bang. By that stage, according to the standard model, galaxies should be small and forming their first generations of stars. Maisie's galaxy, instead, contains billions of stars, organised into a coherent shape, with a mass that should have required a much longer period of growth. Then came others, bigger, older-looking, more mature, some with dust lanes suggesting multiple generations of star formation had already occurred, some with supermassive black holes at their cores, fully grown when black holes that size should not yet have had time to form. One group of galaxies, nicknamed the Impossible Reds by researchers, appeared so red in Webb's images that their light seemed to have come from dense populations of old stars. But those galaxies were seen at a time when there should not have been old stars yet. The universe had not been around long enough to make them. This created what journalists started calling a universe-breaking crisis. To be clear, the word crisis is being used by astronomers themselves in their papers, not just headlines. When Webb's first early universe images were analysed, several teams independently reported that the galaxies they were finding were, in total, too massive to be consistent with the standard model. Not just a little too massive, in some cases, orders of magnitude too massive. One paper in the journal, Nature in 2022, used the phrase breakers of the cosmic model. Another research group calculated that if their measurements were correct, the standard cosmological framework had to be modified because it simply could not produce that much galactic mass in that little time. Other researchers have since pushed back, arguing that some of the early measurements were wrong. Some galaxies turned out to be less massive than initially estimated once their distances were refined. Some of the supposed impossible reds turned out to be closer than first thought, but even after the corrections, a residue of strangeness remains. Enough galaxies are too big, too old, or too developed to explain without modifying some aspect of cosmic evolution. The debates are still unfolding. Papers come out weekly, each with new data, new interpretations, new complications. Some researchers are now suggesting that the very first stars, sometimes called population 3 stars, were far more massive and productive than previous models assumed, seeding the universe with heavy elements and mature galaxies faster than anyone expected. Others are whispering about deeper issues. Maybe the universe is older than we calculated. Maybe expansion proceeded differently in its earliest phases. Maybe we've been miscounting time itself. Each possibility takes us further from solid ground, and one galaxy in particular seems almost to laugh at our confusion. Among Webb's strangest finds is a class of galaxies that appear, in every meaningful way, to be ancient. Their light carries the signatures of long-lived stellar populations, heavy elements forged over many generations, and structures that suggest billions of years of evolution. The trouble is, we are seeing these galaxies as they were when the universe itself was barely an infant. To understand the puzzle, it helps to know a bit about how galaxies age. In a young galaxy, stars are being born rapidly from clouds of hydrogen and helium. These young stars burn hot and blue, flooding the galaxy with ultraviolet light. Over time, the hot blue stars die off, and the galaxy fills up with cooler, redder, longer-lived stars. A mature galaxy looks redder, calmer, and less active in its star formation than a young one. When Webb looks at galaxies supposedly born in the universe's first few 100 million years, it should see vigorous blue starbursts. Hot, chaotic, messy. Instead, some of these galaxies glow with the warm red light of settled, older stellar populations. It is as if Webb has caught a baby with a grey beard. One such galaxy, whose catalogue designation is a string of numbers astronomers shorten in conversation, has been studied in careful detail. Its light suggests a stellar population several 100 million years old, sitting inside a universe that was only about 500 million years old at the time. That leaves almost no margin for the galaxy to have formed, assembled its stars, let them age, and settled into its current appearance. Some researchers have proposed a solution. What if star formation in the very early universe was extraordinarily intense? A burst of rapid formation shortly after the Big Bang could produce a mature-looking galaxy surprisingly fast. This idea, sometimes called early rapid assembly, is not ridiculous. Simulations can be tweaked to produce such bursts under the right conditions, but the conditions required are demanding. You need a lot of dense gas clumped in exactly the right places, cooling and collapsing efficiently into stars, all happening almost immediately after the universe became transparent to light. It is possible, but it borders on conspiracy. Too many things need to go right at once. Other researchers have proposed more drastic answers. Perhaps the cosmic timeline is wrong. Perhaps the universe is older than we think. Perhaps there was a period of accelerated expansion or contraction before the Big Bang that planted early seeds of structure, giving galaxies a head start. Each of these ideas requires rewriting substantial portions of cosmology. There's also the possibility, entertained by a small but growing number of scientists, that these galaxies are not as distant as they appear. If the relationship between redshift and distance were different than current models predict, then a galaxy with a huge redshift might actually be closer, younger, and easier to explain. This would overturn a century of cosmological measurement, but it is a possibility that, quietly, some researchers are beginning to explore. For now, the galaxies sit in the data, glowing redly at impossible ages, refusing to resolve into something simpler. Every new observation adds detail, every new paper tries another explanation. None of them so far fully satisfies the community. And these are just the galaxies Webb can see clearly. Scattered throughout the early universe are even stranger objects, tiny, intense, red, and everywhere. Astronomers have given them a nickname that sounds almost playful: but the questions they raise are anything but. Among the weirdest discoveries Webb has made are objects known affectionately, and sometimes frustratedly, as the little red dots. They show up in Webb's deep field images as compact, extremely red points of light spread across the early universe in numbers nobody expected. At first glance, they seem unremarkable. Small, red, faint. The kind of thing you might scroll past if you were not paying attention. But as astronomers began studying them, their peculiarity became clear. These dots are compact, sometimes extremely so, appearing almost point-like even at Webb's resolution. They are very red, suggesting either a lot of dust, a lot of old stars, or both. And they are populous. Far more of them exist in the early universe than any model predicted. Several possibilities have been proposed for what they actually are. One leading idea is that they are very young galaxies with supermassive black holes at their centres, also known as active galactic nuclei. If true, the black holes would have to have grown with astonishing speed, assembling enough mass to power a bright central engine within just a few 100 million years of the Big Bang. That is faster than any current model allows for black hole growth. Another idea is that the dots are compact starburst galaxies, small but intensely productive, filled with massive young stars that are still shrouded in dust from their formation. In this view, the redness comes from the dust, which absorbs blue light and re-emits it as infrared. But even this explanation has problems, because the dust itself is made from heavy elements that have to be forged by previous generations of stars. If the universe is too young, where did the dust come from? A third possibility, currently being debated, is that the dots are a mixture. Some are young supermassive black holes, some are dusty starbursts, some are exotic objects we do not yet have a name for. Each dot tells a slightly different story, and only with more spectroscopic follow-up will astronomers be able to classify them properly. What makes the dots so challenging is their abundance. If they were rare, they would be interesting curiosities, but Webb finds them everywhere it looks. In the earliest cosmic surveys, the dots appear by the hundreds. Some teams estimate that the total mass they represent is significant enough to affect our overall picture of the early universe's composition. One astronomer described the situation like this. You go looking for a new kind of animal in the woods, and instead of finding one, you discover they're all over the place, which raises a bigger question. How could they be so common, and yet nobody noticed them until now? The answer, of course, is that Webb is the first instrument sensitive enough to see them. They were always there, glowing faintly in the infrared, invisible to older telescopes. Webb did not create them. It simply lifted the curtain. For cosmologists, the dots are both a puzzle and a clue. Each one represents a possible window into an era of the universe we barely understand. Each one might contain a supermassive black hole that should not exist, or a stellar population that grew impossibly fast, or a type of object unique to that distant epoch. And the fastest growing engines inside them suggest that the rules governing black hole formation might need rewriting from scratch. Among the most unsettling findings of the Webb era involves supermassive black holes that appear to have formed far too quickly for the standard cosmological timeline. These monsters, with masses millions or even billions of times greater than the Sun, sit at the centres of galaxies we observe in the universe's first few 100 million years, and their existence challenges everything we thought we knew about how black holes grow. A black hole grows by feeding. It pulls in gas, dust, and occasionally stars, and as matter falls toward the event horizon, the black hole gains mass. There are physical limits to how fast this process can happen. One of them is called the Eddington limit. a boundary set by the balance between gravity pulling matter in and radiation pressure pushing matter out. If a black hole tries to feed too fast, the energy released by infalling matter blows away the surrounding gas, slowing the feeding. Under standard conditions, a black hole cannot exceed its Eddington limit for long periods. This puts a ceiling on growth. Starting from a typical stellar mass black hole, formed by the collapse of a massive star, it should take at least several 100 million years, and often billions, to reach supermassive sizes. Webb has found supermassive black holes at ages where none should yet exist. One such black hole, observed in a galaxy dating to about 400 million years after the Big Bang, already contains about 1.5 million times the mass of the Sun. Another, in a galaxy from slightly later, tips the scales at nearly 1 billion solar masses. These are fully grown giants, and they are sitting in baby galaxies within a young universe. How did they get so big so fast? Several hypotheses exist. One is that these black holes did not start from stellar collapses at all. Instead, they may have formed from the direct collapse of massive gas clouds in the very early universe, creating what are called direct collapse black holes. These could start life already weighing tens or hundreds of thousands of solar masses, giving them a huge head start compared to ordinary black holes. If this is correct, the early universe must have been producing these direct collapse objects abundantly, which changes our picture of primordial physics. Another idea is that these early black holes fed at rates exceeding the Eddington limit for brief periods. This is called super-Eddington accretion, and while it is hypothetically possible under certain conditions, the conditions are exotic. You need dense gas, specific geometries, and environments that are only beginning to be modelled in simulations. The fact that early black holes might routinely break the Eddington limit would be a major revision to our understanding of accretion physics. A third, more speculative possibility is that primordial black holes formed in the first moments after the Big Bang. These would be black holes produced by density fluctuations in the very early universe, before any stars had formed. If they existed, they could have served as seeds for later supermassive black holes, giving them billions of years head start to grow. Primordial black holes have been proposed for decades, but so far no direct evidence has confirmed their existence. Webb's findings may be the closest thing yet. Whichever explanation turns out to be correct, the implication is clear. Our models of black hole formation need revision, and once you start revising one part of a cosmological theory, the rest begins to wobble. The deeper issue, though, is time itself, because the timeline on which all these events must occur is already looking uncomfortably tight. Behind every one of these discoveries sits a deeper worry, not about any individual galaxy or structure or black hole, but about the cosmic clock itself. The age of the universe, calculated from multiple independent methods, comes out to about 13.8 billion years. That number has been one of the most confidently known values in all of cosmology, until now. The problem is that too many things seem to exist too early. Giant structures, mature galaxies, overgrown black holes, dense populations of red dots. Each one individually could perhaps be squeezed into the standard timeline with clever arguments, but together they paint a picture that no amount of squeezing seems to accommodate. There is simply not enough time in the standard 13.8 billion years to produce everything Webb is finding. This has led some scientists to propose something radical. What if the universe is older than we calculated? One particularly striking proposal comes from a researcher at the University of Ottawa, who published a paper suggesting the universe might be 26.7 billion years old, nearly double the currently accepted age. His argument involves a modification to how we interpret light from distant objects. In his framework, some of the redshift we observe is not caused entirely by cosmic expansion, but partly by a phenomenon called tired light, in which photons slowly lose energy as they travel across immense distances. Tired light theories have been proposed many times over the decades, and most have been ruled out by careful observation. But the Ottawa researcher argues that a hybrid model, combining expansion with a small tired light effect, could fit the Webb data better than the standard picture. His proposal remains controversial and is not widely accepted, but the fact that it is being published in serious journals tells you something about the state of the field. Other proposals involve modifications to the expansion history. Perhaps the universe went through a phase of slower or faster expansion that we have not accounted for. Perhaps dark energy, the mysterious force accelerating the universe's growth today, behaved differently in the past. Adjusting the expansion history could add or subtract billions of years from the cosmic age, depending on the details. Each proposal faces stiff resistance from the mainstream. The standard age of 13.8 billion years is based on overlapping lines of evidence, including the cosmic microwave background, the ages of the oldest stars, and measurements of the universe's expansion rate. To change the age significantly, all of those measurements would have to be reinterpreted. But the Webb data keeps piling up, and each new result tightens the vice. Something has to give. Either the galaxies are younger than they look, or they formed faster than we thought, or the universe is older than we thought. There is no fourth option that leaves everything unchanged. In private conversations, some cosmologists now openly say that the age of the universe might be wrong. Not by a small amount, by billions of years. That is a startling possibility, and one that would affect everything from our understanding of stellar evolution to our estimates of how many generations of galaxies have lived and died since the beginning. The clock, in other words, might be off, and if the clock is off, then the whole map of cosmic history might need redrawing. Webb's next images are about to test whether a deeper, stranger pattern has been hiding in plain sight. Step outside on a clear night, away from city lights, and the universe above looks scattered. Stars everywhere. Random, chaotic. But that impression is misleading. When astronomers zoom out far enough, the universe is not random at all. It has a structure, and that structure has a name. The cosmic web. The cosmic web is one of the most beautiful ideas in modern cosmology. Picture a foam of soap bubbles, the kind you might see in a sink full of dishwater. Where the bubble walls meet, the soap film is thin. Where 3 or more bubbles touch, the film thickens into ridges. Where many bubbles come together, it clumps into droplets. The universe is built like that foam. Galaxies are not sprinkled evenly through space. They gather along thin sheets and thicker filaments, with vast empty regions in between. Where many filaments cross, you get dense knots full of galaxy clusters. These are the droplets of the cosmic foam. The empty spaces between them are called voids, and some of those voids are staggering in size. For decades, computer simulations of the universe's growth have reproduced this web pattern with impressive accuracy. Feed a simulation, the known ingredients, ordinary matter, dark energy, and the density variations visible in the cosmic microwave background. Run it forward 13.8 billion years. Out pops a cosmic web that looks remarkably like what telescopes see. This has been one of the great triumphs of the standard model. The fact that simulations match reality so well has given cosmologists enormous confidence in their understanding. But Webb is beginning to reveal places where the match breaks down. When Webb looks at the distribution of galaxies in the early universe, it sometimes sees patterns that do not match simulation predictions. Filaments appearing more connected than expected. Voids either larger or emptier than models predict. Clusters of galaxies grouped more tightly than the Webb theory allows for that epoch. In some cases, Webb has revealed filaments of galaxies so long and straight that they resemble cosmic highways. Thousands of galaxies arranged in orderly strings cutting across regions of space that should have been mostly empty at the time. Our simulations produce filaments, yes, but not filaments quite as bold or well-defined as the ones Webb is uncovering. A team studying one such filament in early 2024 measured its length at about 3 million light-years, packed with galaxies actively forming stars. At first, that might not sound shocking. 3 million light-years is small on cosmic scales, but the key detail is the time. This filament existed when the universe was only about 2 billion years old, a stage when such well-organized structures were supposed to be rare. The implication is that either the cosmic web formed faster than simulations predict, or there is something about the web's assembly we have not captured correctly. These findings are still being digested. The field has not collapsed into panic over them, but they are adding to a growing list of small discrepancies, each one a tiny crack in the foundation of the standard picture. And one particular type of crack, concerning emptiness rather than structure, has caught astronomers' attention because it might apply to our own cosmic neighbourhood. To understand what comes next, we need to spend more time thinking about emptiness. Because the empty spaces in the cosmic web, the voids, are in some ways more mysterious than the galaxies themselves. A void is a region of the universe where galaxies are rare. Not completely absent, but sparse, very sparse. The largest voids can stretch hundreds of millions of light-years across, with only a scattering of lonely galaxies drifting through them. Inside a void, if you were standing on a planet, the night sky would look darker and emptier than anything humans experience from Earth. The nearest neighbouring galaxy might be tens of millions of light-years away, far beyond the reach of unaided eyes. Voids form naturally in the cosmic web. As gravity pulls matter together into filaments and clusters, it also pulls matter out of the spaces between, leaving them progressively emptier. Over billions of years, voids have expanded while structures have compressed, carving out the foam we see today. Most voids are roughly consistent with what models predict. Their sizes and shapes match the outputs of simulations, providing further support for the standard picture. But some voids are not ordinary. Some are anomalously large or anomalously empty. One of the most famous is the Bootes void, discovered in 1981. It stretches about 330 million light-years across and contains far fewer galaxies than cosmologists would expect for its size. At the time of its discovery, it was sometimes jokingly called the Great Nothing. The joke obscured a real puzzle. How did such a huge empty region form? Additional surveys have turned up other large voids. The Eridanus supervoid, also called the cold spot region, because of an associated feature in the cosmic microwave background, is even bigger. Some estimates place it at around 1 billion light-years across. If this void exists and is as large as some measurements suggest, it represents another challenge to the standard model. Supervoids of that scale push the limits of what gravity could have carved in 13.8 billion years. Combined with the megastructures on the other end, enormous rings, arcs, and walls, the universe appears to contain extreme features at both ends of the density spectrum. Too much structure in some places, too little in others. A universe that looks uniform on average, but riddled with extreme features on large scales, is not the universe the cosmological principle describes. It is something messier, richer, and harder to explain. Some cosmologists have begun to wonder if the universe was not simply born smooth and allowed to lumpify through gravity. Maybe it was born with built-in irregularities, seeds of structure and emptiness already present at the start. Maybe the inflationary phase, the brief burst of rapid expansion thought to have occurred just after the Big Bang, produced a less uniform starting condition than our current models assume. If the seeds of giant structures and giant voids were planted at the very beginning, then the universe's foam has always had its shape. We have simply been late to notice. One particular void may be very close to home, and if the measurements are right, we may be sitting inside it. Imagine looking around your neighborhood and realizing it is emptier than most neighborhoods in the city. The streets are wider, the houses are fewer, the distances between them are greater than usual. You'd never noticed before because you grew up there. You had no comparison. That, in essence, is what astronomers now suspect about our corner of the universe. In 2013, a team of researchers, Keenan, Barger and Cowie, published a study that came to be known informally as the KBC void, or the Keenan-Barger-Cowie void. Their analysis suggested that the Milky Way and the galaxies around us sit inside a region of space that is systematically less dense than the cosmic average. Not dramatically so, but measurably. The size of this supposed void is enormous. Some estimates place its radius at around 1 billion light-years, which would make it one of the largest known voids in the universe. If it exists as described, we are living inside an underdense bubble, surrounded on all sides by regions of higher galaxy density. For a long time, the KBC void was controversial. Many astronomers were skeptical. Surveys of galaxy counts are tricky, and calculating average densities over such large scales involves many assumptions. Opponents argued that the void was an artifact of how the measurements were made, not a real feature of space. But over the past few years, additional evidence has accumulated. Measurements of galaxy number counts, comparisons of local and distant expansion rates, and surveys of galaxy distribution have all tended to support the idea that our cosmic neighborhood is less dense than average. The void may be real. If we are indeed inside an underdense region, it has important consequences. For one thing, it could help explain a long-standing puzzle called the Hubble tension, which we'll examine more closely in coming chapters. When we measure how fast the universe is expanding using nearby galaxies, we get one answer. When we measure it using the cosmic microwave background, we get another. The two answers disagree by enough to make cosmologists nervous. A local void might resolve this. If we live in an underdense region, gravity from the denser material outside our void would pull us and our neighbours outward. This would cause us to measure a locally faster expansion rate, which could partly explain why nearby measurements differ from cosmic ones. The void would not fully resolve the Hubble tension, but it could account for some of the gap. The idea is humbling. We've always thought of Earth and the Milky Way and the local group as typical pieces of the cosmos. No special location, no unusual environment. That has been a foundational assumption since Copernicus. If the KBC void is real, it suggests we may live in a slightly atypical region, not at the centre of anything, but inside a larger-than-average emptiness that affects our measurements. The good news is that even if we're in a void, it does not make us cosmically special in any grand sense. Voids are common. Plenty of other galaxies live inside them. It simply means our observations are influenced by our environment more than we had assumed. The bad news is that it adds yet another wrinkle to the standard model, another complication that needs to be accounted for, another reason to question whether the cosmological principle truly applies everywhere. And once you start looking at how galaxies are moving, the cracks widen further. In 2008, a team of astronomers reported something that sounded like science fiction. After studying the motion of galaxy clusters across a huge region of sky, they concluded that many of them were drifting in a specific direction, toward a point beyond the observable universe. The motion was coherent, the velocities were high, and the direction was consistent. They called it dark flow. The idea was explosive. If galaxy clusters were indeed moving together towards something outside our visible cosmos, it implied the existence of massive structures or forces beyond anything we can directly detect. Perhaps even the gravitational pull of other universes in a multiverse, though that interpretation remains highly speculative. Here is how the dark flow team arrived at their conclusion. They used a technique called the kinematic Sunyaev-Zeldovich effect, which measures how galaxy clusters interact with the cosmic microwave background. When a cluster moves relative to the background radiation, its motion imprints a small signature on the background. By measuring these signatures, the team claimed to detect a pattern of movement that could not be explained by known gravitational influences within the observable universe. The initial finding was met with strong skepticism. Other researchers pointed out that the signature was subtle, the statistical significance was borderline, and the interpretation was extraordinary. Subsequent studies, using different techniques and different datasets, produced mixed results. Some confirmed the dark flow, others did not. Data from the Planck satellite, released in 2013, showed a weaker signal than earlier measurements had suggested, leading many to conclude that dark flow might not exist at all. For about a decade, dark flow was considered a probably dead hypothesis. A curious claim that did not survive rigorous testing, but the story is not over. Recent reanalysis, using newer data from galaxy surveys and improved theoretical models, has brought dark flow back into the conversation. Some studies now report residual coherent motions of galaxy clusters that cannot be easily explained by standard cosmology. The effect, if real, is smaller than the original dark flow claim, but it may be genuine. What could cause such motion? Several possibilities exist. One is a massive structure just beyond the edge of our observable universe, pulling galaxy clusters toward it gravitationally. Since the edge of the observable universe is set by how far light has had time to reach us, there's plenty of space beyond that edge where unknown structures might lurk. Another possibility is a remnant from the universe's earliest moments. If the inflationary phase was not perfectly smooth, it could have created enormous density variations at scales larger than our observable volume. The gravitational influence of those variations might pull our region in a particular direction, producing an apparent dark flow. A third possibility, rarely discussed in public but occasionally raised in private, involves physics beyond general relativity. If the law of gravity differs on cosmic scales from what we assume, coherent motions might emerge without requiring hidden mass. This is a minority view, but it cannot be ruled out. The takeaway is not that dark flow is proven. It is that the motion of galaxies on the larger scales may hold clues to physics we have not yet discovered. Clues that Webb and other missions are helping us investigate with new precision. And while we debate what might lie beyond the visible universe, something hidden much closer to home continues to pull entire galaxies in its direction. Some cosmic mysteries are far away, Others are disturbingly close. The Great Attractor falls into the second category. It is a gravitational anomaly in our own local universe, pulling our galaxy and thousands of others toward it, and for decades it was hidden from our view by an inconvenient obstacle, our own Milky Way. The story begins in the 1970s, when astronomers first noticed that our galaxy was moving with respect to the cosmic microwave background. The motion was fast, about 370 miles per second, and it pointed in a particular direction in the sky. Further observations revealed that not just the Milky Way, but our entire local group of galaxies and the Virgo supercluster beyond it were all moving in the same direction. Something was pulling us. When astronomers tried to look where the pull was directed, they ran into a problem. The direction pointed toward a region of sky behind the central plane of the Milky Way, where dust, gas, and stars of our own galaxy blocked the view. This region is called the zone of avoidance because optical astronomy cannot see through it easily. It was, and largely still is, a cosmic blind spot. Whatever was pulling us sat in that blind spot. For years, astronomers had no direct way to see what it was. They gave it a name that reflected their ignorance: the Great Attractor. Over the decades, improved techniques, particularly radio and infrared observations that can pierce through our galaxy's dust, have given us partial views. The Great Attractor turned out to be a dense concentration of galaxies, a massive supercluster sitting about 150 million light-years from us. Its gravitational pull on our local universe is real and measurable. But the story got stranger. Further observations revealed that the Great Attractor itself is moving, being pulled by something even larger and farther away. That something is now called the Shapley supercluster, a collection of galaxy clusters about 650 million light-years from Earth. It is one of the most massive structures ever identified, and it sits at the center of a larger region of higher than average density. All of this connects to a discovery made in 2014 called Laniakea, our home supercluster. Laniakea includes the Milky Way, the Virgo supercluster, the Great Attractor, and many other galaxy groups, all bound together by the gravitational flows of the region. We did not even know we lived in Laniakea until recently, because its boundaries only become clear when you trace the motions of galaxies across huge volumes of space. What the Great Attractor reveals is that the local universe is not uniform. It has dense knots and voids, gravitational wells and peaks. We are being pulled by forces we cannot always see toward objects we cannot always observe, and we are part of a larger flow that stretches across hundreds of millions of light-years. This matters for cosmology because it complicates our measurements. When we observe the rate of expansion, we have to account for local flows like the one pulling us toward the Great Attractor. Subtract that motion out and we get a cleaner picture of cosmic expansion. But if our corrections are wrong, our expansion measurements will be off. The Great Attractor, combined with our possible residence inside the KBC void, suggests a universe where local environment matters more than we once thought, where the cosmological principle applies only on scales larger than we can easily sample. And if local motion affects measurements, what about the spin of the universe itself? Because evidence for that has started appearing in Webb's most distant images. In early 2025, a researcher at Kansas State University published a paper that turned heads across the astronomy community. After analysing hundreds of galaxies in Webb's deep field images, the researcher reported an unexpected pattern. The galaxies seemed to show a preferred direction of rotation. To appreciate why this is strange, you need to know what the standard expectation is. Galaxies rotate, of course, spiral galaxies spin around their centers. But the direction of rotation, clockwise or counterclockwise from our viewpoint, should be random. Half the galaxies in any large sample should appear to rotate one way. The other half should appear to rotate the other way. When you count them up, the numbers should balance. The Kansas State study found they did not balance. Among the galaxies observed by Webb in one particular deep field, a meaningful majority appeared to rotate in the same direction. The imbalance was too large to be explained by random chance. The researchers' interpretation was striking. Perhaps the universe itself is rotating. Perhaps it was born with a net angular momentum, inherited from some larger structure or process that preceded the Big Bang. If the universe has a preferred axis, galaxies embedded within it might inherit a bias in their spin directions. This would be a revolutionary finding. The standard cosmological models assume the universe has no preferred direction. A rotating universe would violate that assumption, requiring major modifications to the theories we use to describe its evolution. Before anyone gets too excited, though, it is important to note the caveats. The Kansas State result is based on a single dataset and a specific method of analysis. Other researchers have pointed out possible biases. The sample may be too small. The rotation direction might be easier to detect for certain galaxy orientations than others. More data is needed before the claim can be confirmed or rejected. Other studies have found weaker versions of similar effects. Analyses of galaxy orientations in various surveys have occasionally turned up small, statistically significant deviations from perfect randomness. These hints have been debated for years, with no clear consensus on whether they are real or artifacts. If the rotation is real, several interesting possibilities open up. One is that the universe emerged from a parent universe that was already rotating, and inherited that rotation at its birth. This is sometimes called the rotating universe hypothesis, and it has been explored mathematically for decades. Another is that the rotation is a remnant of quantum fluctuations during the inflationary phase, blown up to cosmic scale. A third is that it reflects some deeper structure of space-time that current physics does not fully capture. All of these ideas are speculative. None has been confirmed. But the fact that Webb is producing data precise enough to test such questions is itself a remarkable achievement. A decade ago, we could not have run this kind of analysis. Today, we can, and the results are open enough that serious debate is ongoing. If even one of these ideas turns out to be correct, it would mean the universe has a shape, an orientation, a set of intrinsic properties that go beyond what the standard model describes. And a curious pattern in the very oldest light we can detect has made some scientists wonder if that possibility is already written across the sky. Long before Webb began producing unsettling results, another instrument had already hinted at anomalies in the universe's largest features. That instrument was the Wilkinson Microwave Anisotropy Probe, followed by the Planck satellite. Both mapped the cosmic microwave background, the faint afterglow of the Big Bang, in exquisite detail. The cosmic microwave background, or CMB for short, is essentially a photograph of the infant universe. It shows tiny variations in temperature across the sky, caused by small density differences in the early universe. Most of these variations look random, consistent with the predictions of standard cosmology. But a few features look too organized. When astronomers analyzed the patterns in the CMB, they noticed that certain large-scale features appeared aligned. Specifically, some of the broadest temperature variations seemed to point along a particular axis. This axis became known with dark humor as the axis of evil. The name was meant to capture how troublesome the finding was. If the cosmic microwave background has a preferred axis, it suggests the early universe was not perfectly uniform. It had a direction. And that direction, according to several independent analyses, happens to align suspiciously well with the orientation of our solar system. That alignment set off alarm bells. Any result that seems to make Earth, or the solar system, a special location in the universe is automatically suspicious. Either the result is wrong, or something very strange is going on. For more than a decade, researchers have tried to determine which it is. Some have argued that the axis of evil is a statistical fluke, a pattern that looks meaningful but arises from the random noise in the data. Others have pointed to possible systematic errors, subtle biases in how the CMB was measured or processed. Still others have taken the results seriously and proposed that the early universe really did have a preferred direction, perhaps set by whatever physics preceded the Big Bang. The Planck satellite, launched to provide more precise CMB measurements, largely confirmed the existence of the anomalies first seen by WMAP. The axis of evil did not go away with better data, it stayed. This surprised many cosmologists who had hoped better measurements would erase it. If the axis of evil is real, it raises uncomfortable questions. How could the early universe have a preferred direction? Standard inflationary models say it should not. Any initial asymmetries should be smoothed out during inflation. For a preferred direction to survive into the CMB, something in the inflationary process must have failed, or something unusual must have happened before inflation began. Some cosmologists have proposed connections between the axis of evil, the possibility of a rotating universe, and other large-scale anomalies. If all of these point to the same underlying feature, we may be seeing the fingerprint of a cosmic property we've not yet understood. The scientific community remains divided. Mainstream cosmologists tend to treat the axis of evil as an unexplained curiosity, probably statistical, possibly real, but not yet a crisis. A minority of researchers treats it as evidence for new physics, a clue pointing toward a deeper understanding of cosmic origins. Either way, the anomaly remains in the data, stubborn and suggestive, reminding us that even the oldest light we can see may carry messages we have not fully decoded. The Big Bang is often described as the beginning, the moment when time, space, and matter came into existence. Before the Big Bang, we're told, there was nothing. No time, no space, no anything. But the evidence from Webb and from other cosmic anomalies is pushing some scientists to reconsider this picture. If structures too large to form within 13.8 billion years actually exist, and if the cosmic microwave background shows patterns that standard inflation cannot explain, and if the universe might have a preferred direction or a rotation, then something must have been happening before the Big Bang that set the stage for what we see today. This is not a fringe idea anymore. Several serious physicists have proposed models in which the Big Bang is not a true beginning, but a transition. A moment when a prior state of the universe gave way to the state we currently observe. These pre-Big Bang models come in several flavors, and Webb's findings are giving them new life. One family of theories is called cyclic cosmology. In these models, the universe goes through repeated cycles of expansion and contraction. Each Big Bang is preceded by a big crunch, in which a previous universe collapses and bounces back into a new expansion. If this is the case, the structures we observe might be partly inherited from the previous cycle. Galaxy clusters, cosmic webs, and large-scale anomalies might carry memories of an earlier universe. Another family of models involves the idea of eternal inflation. In these scenarios, the inflationary phase of the universe never fully ended. Instead, it continues eternally in different regions, with our observable universe being just one bubble among many. Bubble universes can collide, and when they do, they leave imprints on the cosmic microwave background. Some researchers have searched for these imprints and reported possible candidates, though none has been confirmed. A third, more speculative framework is the cyclic universe proposed by Roger Penrose, called conformal cyclic cosmology. In this view, the heat death of one universe, the ultimate fate when everything has decayed into low-energy radiation, becomes the Big Bang of the next. Penrose has argued that faint rings in the cosmic microwave background might be evidence of events from the previous universe, preserved across the transition. The claim remains highly controversial, but it is being taken seriously by some researchers. Each of these ideas requires new physics. Each requires us to accept that the Big Bang is not the ultimate origin, and each is made more plausible, or at least more interesting, by the Webb discoveries. If the early universe already contained mature galaxies, impossibly large structures, and a preferred direction, it becomes harder to argue that it all started from a perfectly smooth, featureless beginning. Something must have been set up in advance. Some process must have planted the seeds of structure before the standard Big Bang timeline even begins. This does not mean we know what was before. It means the door to the question is being reopened. Physics beyond the Big Bang is no longer just philosophical speculation. It is becoming a target for serious theoretical and observational work. Whether we will ever be able to directly probe what came before the Big Bang is uncertain. The earliest moments after the bang are hidden from view by the opaque plasma that filled the universe at the time. Light cannot reach us from before that era, but gravitational waves might. Certain exotic signatures in the cosmic microwave background might. And structures in the observable universe, if they retain imprints of pre-bang physics, might too. And one reinterpretation of distant galaxies has scientists asking whether the standard timeline of cosmic history was always a story we chose, not one the universe confirmed. For most of the 20th century, cosmology was a highly consensus-driven field. The standard model, with its Big Bang, expanding universe, and dark matter and dark energy components, enjoyed broad support among professional astronomers. Alternative theories existed, but they were largely dismissed as fringe. Webb's findings are changing the conversation. Ideas that were once considered outside the mainstream are being re-examined with fresh eyes. Not because the mainstream is being abandoned, but because the data is forcing scientists to consider possibilities they had previously set aside. One such idea is tired light. First proposed by Fritz Zwicky in 1929, tired light theory suggests that photons lose energy as they travel across vast cosmic distances. If this happens, the redshift of distant galaxies would not be entirely due to the expansion of the universe, but partly due to photons tiring out along their journey. Under this interpretation, the universe might not be expanding as fast as we think, or it might be older than the current estimate of 13.8 billion years. Tired light fell out of favour decades ago because it seemed to conflict with various observations, including the shape of the cosmic microwave background and the way supernovae brightness relates to distance. But some modern proponents argue that hybrid models, combining a small amount of tired light with cosmic expansion, could reconcile Webb's findings with a revised timeline. The Ottawa researcher we mentioned earlier suggests exactly this, arguing the universe might be nearly twice its standard age. Another reconsidered idea is the bouncing universe. In these models, the Big Bang was preceded by a contraction phase, and the universe oscillates between expansion and contraction over cosmic time. Bouncing cosmologies can explain why our universe appears flat and uniform without invoking inflation. They also naturally predict that some features of our current universe were inherited from the previous cycle. Loop quantum cosmology, a branch of physics inspired by attempts to combine quantum mechanics with gravity, has produced specific bouncing models with testable predictions. Some researchers have argued that certain features of the cosmic microwave background are more consistent with a bounce than with traditional inflation. The debate is active and ongoing. A third idea gaining renewed attention is modified gravity. The standard model assumes that general relativity, Einstein's theory of gravity, is correct on all scales. But some observations, particularly those involving dark matter, hint that gravity might behave differently on galactic and cosmic scales than Einstein predicted. Modified gravity theories such as modified Newtonian dynamics, or MOND, have been proposed to explain some observations without invoking dark matter at all. Webb's data is adding to this conversation. Some discoveries are easier to explain if gravity behaves slightly differently on certain scales. Others resist easy explanation under any framework. The field is increasingly open to the idea that multiple modifications might be needed, not just one. None of these fringe theories has been established. All of them face significant challenges, but the willingness of serious scientists to consider them reflects the discomfort in the field. When the standard model keeps running into problems, even ideas that were long dismissed deserve a second look. Cosmology in the Webb era feels a bit like medicine during the germ theory revolution. For decades, certain ideas were accepted as obvious. Then new tools, microscopes in that case, Webb in ours, revealed a deeper level of reality. Some long-held beliefs survived, others did not. The exciting and terrifying part is that we are still in the middle of that process, and in the middle of that process, another measurement refuses to stop disagreeing with itself. Let's talk about one of the most serious puzzles in modern cosmology, something called the Hubble tension. It is less flashy than a billion light-year ring, but in many ways it is even more troubling, because it involves a fundamental quantity, the rate at which the universe is expanding. When we measure how fast the universe is expanding, we get different answers depending on which method we use. One approach uses the cosmic microwave background. By analysing the patterns of temperature variation in that ancient light, cosmologists can calculate what the expansion rate should be. This gives a value of about 67 kilometers per second per megaparsec. Do not worry about the units, the key thing is the number 67. The other approach uses nearby objects, particularly a type of exploding star called a Type 1a supernova, combined with carefully calibrated distance measurements. These local observations give a different value, about 73 kilometers per second per megaparsec. 67 versus 73, a difference of roughly 8%. That might not sound like much, but in cosmology, it is enormous. Modern measurements are precise enough that a difference of 8% cannot be waved away as measurement error. The two methods are both claiming high accuracy, and they're giving answers that statistically should not agree if one of them is wrong. This disagreement is called the Hubble tension, and it has been troubling cosmologists for over a decade. At first, many assumed it would go away with better data. If anything, better data has made it worse. Every new measurement has refined the values without bringing them closer together. Possible explanations have multiplied. One possibility is that something is wrong with our measurements of the cosmic microwave background, perhaps due to unknown astrophysical effects. Another is that something is wrong with our local distance measurements. perhaps due to biases in how we calibrate supernova. Yet another is that dark energy behaves differently than we think, changing in strength over time in ways that affect expansion. Some researchers have proposed that new physics is needed. Maybe there is a new kind of dark energy, active only in the early universe, that modifies how the cosmic microwave background is interpreted. Maybe dark matter has interactions we've not yet accounted for. Maybe the universe went through phases of different expansion behavior that our models do not fully capture. Webb has added fuel to this fire. Some of its measurements of distant galaxies, when used to infer cosmic expansion, have returned values consistent with the local measurement of 73, reinforcing the tension. Other measurements support 67. The data is producing contradictory results, and nobody yet knows which to trust. If the Hubble tension is real, it means one of the cornerstones of modern cosmology is cracked. The expansion of the universe is the most fundamental parameter we measure. If we cannot agree on how fast it is expanding, we cannot agree on its age, its size, its composition, or its future. Some scientists suspect the tension will be resolved in the next decade with even better measurements. Others think it will lead to a revolution, forcing us to modify our fundamental models. The debate is heated and the stakes could not be higher, and just when the tension seemed to be our main expansion puzzle, Webb has delivered a new measurement that appears to settle one debate while opening another. In 2024, a team using Webb's precise infrared measurements of nearby galaxies published a result that many had been waiting for. They had refined the local measurement of the Hubble constant using Webb's superior capabilities, and they expected to find that the tension would shrink. Instead, the tension stayed, and in some analyses, it appeared slightly larger. The team used Webb to observe a type of star called a Cepheid variable in several nearby galaxies. Cepheids are pulsating stars whose brightness varies in a predictable way, making them excellent distance markers. By measuring Cepheids with Webb's precision, the team hoped to settle lingering questions about whether older measurements had systematic errors. The results confirm the earlier local measurements. The expansion rate in our cosmic neighborhood is about 73, not 67. The discrepancy with the cosmic microwave background measurement is real and not easily dismissed. This was a major blow to those who had hoped the tension would go away. It was also a major boost for those who believe the Hubble tension points to new physics. Webb's confirmation has several implications. First, it rules out certain explanations for the tension. If local measurements had been wrong, Webb's more precise observations would have revealed the error. They did not. The local value of 73 stands firm. Second, it sharpens the focus on other possible explanations. Either the cosmic microwave background measurement is wrong, or something about the universe's evolution between then and now is different from what we assume. The first option would require us to reinterpret the CMB data, which cosmologists are generally reluctant to do because that data has been studied exhaustively. The second option would require new physics. Third, it raises the possibility that local effects, such as our residence in the KBC void, may be contributing to the difference. If we live in an underdense region, our local expansion measurement could be faster than the cosmic average, not because the expansion is truly faster here, but because we are being pulled outward by the denser surroundings. Some researchers have argued that this could account for most of the tension. Others disagree, suggesting that a void of the required size is unlikely given other observations. The conversation is unresolved. Papers continue to appear on both sides. Conferences feature lively debates, and while scientists argue, the rest of us are left to wonder what the truth actually is. One thing is clear. The universe is telling us something, and we are not yet fully understanding the message. The expansion rate disagreement might be a symptom of a deeper issue. Maybe the universe is not as simple as our models assume. Maybe space itself has properties we have not yet identified. Webb was supposed to bring clarity. In some ways, it has. It has ruled out certain explanations and confirmed certain measurements. But it has also deepened the mystery, revealing that the Hubble tension is not a fluke waiting to disappear, but a persistent feature of our observations. What comes next depends on future missions, future analyses, and future ideas. But the fact that Webb has brought us to this point, where the biggest questions in cosmology are actively in flux, is itself a sign of how powerful this telescope has been. And one of those biggest questions may have an answer sitting in the mysterious force driving the cosmos apart. Dark energy is the mysterious force that drives the universe's accelerating expansion. We do not know what it is. We know it exists because we observe its effects. Distant supernovae appear fainter than they should if the universe were expanding at a constant rate, which tells us the expansion is accelerating. Something is pushing space apart, and that something is dark energy. For a long time, the simplest assumption was that dark energy is constant, a fixed property of space, pushing with the same force everywhere and at all times. This assumption is built into the standard model as a parameter called the cosmological constant. But recent measurements suggest that dark energy might not be constant after all. It might be changing over time. The most striking evidence comes from the dark energy spectroscopic instrument, known as DESI. DESI is a survey that measures the positions and velocities of millions of galaxies across a huge volume of space, creating the most detailed map of cosmic structure ever produced. By studying how galaxies are distributed across time, DESI can reconstruct how dark energy has behaved throughout cosmic history. In 2024, DESI released preliminary results that rattled the cosmology community. The data suggested with moderate statistical confidence that dark energy may have been stronger in the past and weakened over time. This would mean dark energy is not a constant but evolves. If confirmed, this finding would overturn a core assumption of the standard model. It would require us to think of dark energy not as a fixed feature of space, but as a dynamic entity with its own history and behavior. This idea has been proposed before, under various names such as quintessence, but it has lacked strong observational support until now. DESI's results are preliminary. More data is expected in coming years that could either confirm or rule out the evolution of dark energy. The cosmology community is watching closely. If the result holds, it will be one of the most important discoveries in physics in decades. The implications of evolving dark energy are profound. If dark energy is changing, the fate of the universe could be different from what the standard model predicts. Current models suggest the universe will continue to expand forever, cooling into eternal darkness as galaxies recede beyond our horizon. But if dark energy evolves, the future could look different. Expansion might slow, it might accelerate faster. It might even reverse, leading to a big crunch. Evolving dark energy could also explain some of the other anomalies we have discussed. The Hubble tension might be partly due to dark energy behaving differently at different epochs, affecting how we interpret measurements. The early maturity of galaxies might be partly due to different expansion rates in the distant past, giving galaxies more time to grow than we thought. All of these ideas are speculative at this stage. Scientists are cautious about declaring victory for any particular interpretation, but the fact that serious data is now suggesting dark energy changes over time is itself a major shift. Until recently, the idea was a minority view held by a few theorists. Now it has observational support that cannot be ignored, and the survey that produced that evidence has shaken the very foundations of cosmology. The Dark Energy Spectroscopic Instrument, or DESI, is one of the most ambitious surveys in the history of astronomy. It sits atop Kitt Peak in Arizona, where a specialized telescope captures light from millions of galaxies, quasars, and other cosmic objects. Each observation provides information about how these objects are distributed across the universe and how they have moved over cosmic time. DESI is designed to answer one big question: how has dark energy behaved throughout cosmic history? By mapping galaxies at different distances, DESI can reconstruct the expansion history of the universe with unprecedented precision. Different dark energy models predict different expansion histories, so DESI's map can distinguish between them. The first major DESI results came out in 2024, and they delivered a shock. The data was consistent with an evolving dark energy model, not a constant one. The statistical significance was around 3 to 4 sigma, meaning there is only a small probability, roughly 1 in 1,000, that the result is due to random chance. In physics, 3 sigma is considered interesting. 5 sigma is considered a confirmed discovery. The DESI result sits somewhere in between, strong enough to take seriously, not strong enough to be final. Cosmologists around the world began dissecting the DESI data. Some were excited, some were skeptical, some were worried. If DESI is right, it is not just dark energy that changes. It is the entire framework of cosmology. The standard model of the universe has dark energy as a constant, and that constant has been used to calculate everything from the age of the universe to the distribution of galaxies. If the constant is not constant, many calculations need to be redone. The scientific process is now playing out. More data is being collected. Other teams are running independent analyses. Theoretical physicists are developing new models to explain what DESI might be seeing. The next few years will determine whether the evolving dark energy result survives further scrutiny or fades under new observations. If it survives, it will trigger what is sometimes called a paradigm shift, a moment when the field officially recognizes that the old framework no longer fits the data and a new framework is needed. Paradigm shifts in cosmology are rare. The last one was probably the discovery of cosmic acceleration in the late 1990s, which introduced dark energy into the standard model in the first place. A new paradigm shift involving dynamic dark energy would reshape the field. Textbooks would need updating. Theoretical research would pivot. New observational programs would be designed to test the new framework. It would be a thrilling and disruptive time in cosmology. For now, we wait. DESI continues to collect data. Other surveys, such as the Nancy Grace Roman Space Telescope and the Euclid mission, will add their own observations over the coming years. Together, these missions will either confirm DESI's hint of evolving dark energy or show that it was a statistical fluctuation. Either outcome will be informative. If evolving dark energy is confirmed, we enter a new era of cosmology. If it is rejected, we learn that dark energy really is constant, and we must look elsewhere for explanations of the anomalies Webb has revealed. The story is still being written, and it is not just scientists who would feel the impact of what comes next. Imagine being a student in the year 2030. You open your astronomy textbook, and the first few chapters look nothing like the textbook your parents used. The age of the universe is listed differently. The composition of the cosmos includes new components. The diagrams of cosmic history have been redrawn. Familiar terms have been replaced with unfamiliar ones. This is not an idle imagining. It is a real possibility if the anomalies we have discussed turn out to reflect genuine gaps in our understanding. If the cosmological principle is found to apply only on scales larger than we currently probe, textbooks will need to explain cosmic structure differently. The idea of a uniform universe will have to be replaced with a more nuanced picture, where large-scale irregularities exist but average out on still larger scales. If dark energy is confirmed to change over time, the standard model will be replaced with a model that includes dynamic dark energy. Chapters on the fate of the universe will need rewriting. Predictions about cosmic expansion will need revising. The simple concept of a cosmological constant, which has appeared in physics textbooks for a century, will become a historical footnote. If the Hubble tension is resolved by new physics, textbooks will need to introduce that physics to students. What that new physics looks like depends on which explanation wins, but whatever it is, it will likely involve concepts unfamiliar to most of today's readers. If the age of the universe turns out to be different from 13.8 billion years, the entire timeline of cosmic history will need updating. Key milestones, the formation of the first stars, the reionization of hydrogen, the assembly of galaxies will shift in time. Textbooks will need to reconsider when everything happened. Beyond textbooks, the cultural impact could be substantial. The standard model of cosmology has become part of popular understanding. Documentaries, books, museum exhibits, and educational programs all rely on its framework. If that framework changes significantly, all of this content will need updating. Scientists themselves would face a period of adjustment. Careers have been built on studying the standard model. Research grants have been awarded to explore its implications. If the model changes, researchers will need to pivot, learning new tools and adopting new questions. Some will welcome the shift, others will resist it. History shows that paradigm changes in science are often accompanied by generational transitions, with older researchers holding on to the old paradigm, while younger ones embrace the new. There is another, more philosophical implication. If the standard model is wrong in significant ways, it suggests that our confidence in our understanding of the cosmos has been misplaced. For decades, we've presented cosmology as a largely solved problem, with only the details to fill in. A major revision would force us to acknowledge that we were wrong, that the universe is more complicated and mysterious than we had claimed. This is not necessarily bad. Science advances by discovering its own errors. Every revolution in understanding has been preceded by the recognition that previous ideas were incomplete. Humility about the limits of our knowledge is a healthy attitude for a scientific field. Whether we are about to experience such a revolution or not, the possibility is real, and living through it would be one of the most exciting periods in the history of cosmology. At the center of this uncertainty, though, lies a more uncomfortable admission. Our confidence might have been built on assumptions that were always shakier than we let on. Here is a possibility that makes cosmologists uncomfortable, and that deserves honest consideration. What if the standard model of cosmology was never fully correct? What if we built an elegant framework that fit the data we had, but the data we had was limited, and the framework happened to match by luck or by approximation? Science works by building models that explain observations. If the observations are limited, the model might be approximately right without being fundamentally right. As more observations come in, approximations that once seemed solid can reveal themselves to be incomplete. What was once the best available theory becomes a special case of a more general theory, or an outright wrong idea that gets replaced. This has happened many times in physics. Newton's laws of motion were the best available theory for over 200 years. They were not wrong in the sense of being useless. They worked beautifully for most everyday situations, but when careful measurements revealed anomalies, such as the precession of Mercury's orbit or the behaviour of light at high speeds, it became clear that Newton's laws were a special case of a deeper theory. That deeper theory was Einstein's general relativity, which superseded Newton's framework on cosmological scales while preserving it for everyday use. Could something similar be happening now? Could the standard model of cosmology be a useful approximation that is breaking down under the weight of new, more precise observations? Many researchers suspect it might be. The accumulation of anomalies, Webb's impossible galaxies, DESI's evolving dark energy, the Hubble tension, the megastructures, the axis of evil, and so on, suggests that our current framework is being stretched beyond its design limits. A deeper theory might make all these anomalies disappear. It might explain the megastructures, the mature early galaxies, the evolving dark energy, the Hubble tension, and other puzzles as natural consequences of a more complete picture. Such a theory would not invalidate the standard model entirely, because the standard model works well enough in most regimes, but it would supersede the standard model the way general relativity superseded Newton. What would this deeper theory look like? Nobody knows yet. It might involve modifications to gravity on cosmic scales. It might involve new forms of matter or energy we have not detected. It might involve a different understanding of time or space or causality. It might involve physics inherited from a pre-Big Bang era. The possibilities are many, and the correct answer has not yet emerged. What seems increasingly likely is that the standard model, as currently formulated, will not survive intact. Either it will need significant modifications to account for new data, or it will be replaced by a new framework that we can barely glimpse today. This is the exciting part of cosmology in 2026. We're at a moment when the old framework is visibly strained, but the new framework has not yet arrived. We're in a transition period. Papers are being written, debates are raging, new observations are coming in almost weekly. It feels to those inside the field like a moment of genuine scientific progress, even if the progress is uncomfortable. For those of us watching from the outside, it is a chance to witness science doing what science is supposed to do: test its own ideas, challenge its own assumptions, reveal its own limits, and eventually arrive at a deeper understanding than before. The final question, though, is not whether our models need updating. It is whether the universe is stranger than any model we build could ever capture. We have travelled far in this journey. From the moment astronomers first saw Webb's shocking image, through the forbidden giants and impossible galaxies, to the deep structural puzzles of expansion, dark energy, and cosmic shape. Along the way, we have encountered rings that should not exist, walls that break the rules, black holes that grew too fast, and galaxies that look older than their own age. And we have asked hard questions. What if the cosmological principle is wrong? What if the universe is older than we think? What if dark energy changes over time? What if there was physics before the Big Bang? These questions do not have final answers yet. The field is in motion. New data is coming in. New theories are being proposed. The ground is shifting under cosmology's feet, and we're all witnesses to the shift. But there is a deeper question underneath all of these, a question that haunts every scientific investigation of the cosmos. Is the universe, at its deepest level, comprehensible to creatures like us? We are apes who have evolved on a small rocky planet. with brains shaped by the pressures of survival in an African landscape. Our senses detect only a narrow slice of what exists. Our brains evolved to solve problems like finding food and avoiding predators, not to understand the structure of space-time on cosmic scales. The fact that we understand as much as we do is remarkable, but the fact that we reach limits, moments when our tools and theories fail, is also entirely expected. Maybe the universe has features we cannot directly perceive because they are too large, too small, too fast, too slow, or too different from anything our senses evolved to detect. Maybe some of the anomalies Webb is revealing are hints of those features. Maybe the path to understanding requires us to build instruments and frameworks of thought that go beyond what has served us so far. This is the most honest way to frame the current moment. We do not know how much of the universe's strangeness we can capture. We do not know what tools or theories will be needed to capture more. We do not know whether the deepest truths of the cosmos will yield to our investigations or remain forever beyond our reach. What we do know is that we keep trying, telescope after telescope, theory after theory, question after question. Each one teaches us something, even when it raises more questions than it answers. The Standard Model taught us about cosmic expansion, galaxy evolution, and the behavior of matter across billions of years. Even if that model is superseded, its lessons will not be lost. They will be absorbed into whatever comes next. Webb is one chapter in this ongoing story. It will not be the final chapter. Other telescopes are being built. The extremely large telescope in Chile will begin observations in coming years. The Nancy Grace Roman Space Telescope will launch and survey the sky with unprecedented efficiency. Ground-based surveys will map billions of galaxies. Gravitational wave observatories will detect ripples in space-time from events no one has witnessed before. Each of these instruments will reveal new pieces of the puzzle. Some will confirm current theories, some will challenge them, and together they will paint a picture of the universe that is richer, stranger, and more layered than anything we can imagine today. So we end where we began, with a question, not an answer. The universe is stranger than our models predicted, maybe stranger than our models can ever predict. And in that strangeness, there's room for discovery, for wonder, and for the quiet thrill of knowing that we have barely begun to understand where we live.